Hello and welcome to our next lecture. Today we're talking about the discrete Fourier transform, which is the mathematical background behind the digital revolution we enjoy today. So far we talked about the Fourier transform as a transformation that takes a function from the time domain and transforms it into another function in the frequency domain. We also talked about the Fourier series as a transformation that takes a function from the time domain and transforms it into a series of coefficients. So far, if we think about a function f of t in the time domain, it's a function that undergoes a certain evolution. And then the Fourier transform transforms it into a function f hat of omega, which is a complex function. I'm going to plot something like just the real part of it. The Fourier transform is invertible. So if we know the function, we can compute the spectrum. If we know the spectrum, we can compute the function. On the other hand, if we know that the function f of t has a limited domain, say 0 to L, then it can be represented by a Fourier series which means that the coefficients ck are just sampling the Fourier transform at the point 2 pi k over L. So it looks like we transform function f of t into a numerical sequence ck, which is basically the full spectrum of f at the point 2 pi k over L. The effect that it has on the function is that the function now becomes periodic with a period L. So in fact, we're creating ghosts of the function. When we represent the function f of t with a series, increasing L means increasing the frequency of the sampling. The larger the interval 0 to L is, the more frequent are the samples from the actual Fourier transform of the function. And it means that the repetitions of the function grow wider apart. So if we sample the function, so sin is non-zero on some interval, and then we just take the samples of the function at some predetermined frequency. So a sample fk is a function at some predetermined time tk, and tk is just a multiple of the little distance from 0. So if h is the interval between the samples, then the kth sample is just k times h. So if we sample the function, then we can create a periodic representation of the Fourier spectrum. So now f hat of omega is going to be the sum of fk e to the minus I omega times tk. So what that would do is it would create a periodic representation of the Fourier spectrum of the function. And the period will depend on the sampling frequency. So increasing sampling frequency means increasing the period of f hat of omega. In this representation, here lies a question. We know function with the finite time domain, the spectrum has an infinite frequency domain. So how does those repetitions are created? Whether or not the spectrum was chopped at minus b to b and then repeated, or whether or not something different happens. What actually happens is the periodized spectrum that we create with this representation, with this sampling process, will actually be a summation of the shifted copies of the spectrum, something I will explore a little bit later with my examples. What if we try to sample both the function and the spectrum? By the way, we can never have infinitely many samples, so at this point I'm going to specifically assume that the sampling is finite in both time domain and the frequency domain. So suppose I have a function on the interval 0 to L, and I sampled it with my samples fk. That created a periodized spectrum of the function. And I will only sample my periodized spectrum on one period and ignore the other period. So I will call this f hat k. So the questions arise: will I be able to correctly represent the signal with the samples of only the first period of the Fourier transform? And the answer to that is affirmative, given a certain condition on the spectrum. Here's another concern that we have. Well, knowing that sampling of either the time domain function or the Fourier spectrum creates periodic copies in the opposite domain, then what we actually did is we also periodized the signal, at least theoretically, in the time domain as well. And this periodization of both function and the spectrum may create problems or may be actually very useful in certain applications. So for example, when you're trying to sample sound, knowing that there is a periodic shift and addition of the spectrum, if you don't want the higher frequencies influence the lower frequencies that will come from such periodic addition, then people very often filter the high frequencies from the signal so they don't penetrate into the lower spectrum when you do your sampling. If you want to know a little bit more about this, you can research any resources that talk about aliasing when sampling an audio signal. This is also used in the digital communication to an advantage. If you operate on extremely high frequencies, then you can actually sample with very low frequency, because by doing so, when the spectrum is periodized, the high frequencies that you're trying to sample actually migrate into the lower frequency regions, and you can have a pretty accurate representation of the signal with very low frequency sampling. So enough of exposition and introduction to the topic. Let's talk about the definitions and theorems. So suppose I have a vector of samples, f0, f1, f2, etc., 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 up to fn minus 1. If you start numeration at 0, then you should add an n minus 1 to create exactly n samples. If the samples are real, this is in the space Rn. If they're complex, then they're in the space Cn. We define the discrete Fourier transform of f as a vector f hat from the space of complex numbers with components f hat kth will be the sum. We take every sample fj and multiply it by minus 2 pi I k over capital N j. Since we have samples going from 0 to n minus 1, this is the range of summation. You can see here the quantity 2 pi I k over n plays the role of the frequency, and j kind of plays the role of the time. We can, if we want to, consider k as a continuous variable, and this way we'll create a function in the spectrum domain. We'll explore this a little bit later in the examples. So before we had a complex exponential basis of functions, and we were representing the function from the time domain as a summation. This time we're representing the spectrum of the function as a summation, so it's kind of similar to what we did in the complex Fourier series. To prove that this transform is invertible and that the signal and the Fourier transform represent each other perfectly, we will need some preliminary results. So to begin with, I'm going to define vectors that I'm going to denote as capital W kth that will have quantities e to the 2 pi I k over capital N raised to different powers. So j goes from 0 to n minus 1, and that's exactly what I'm going to do. I'm going to have this number in the power 0, then raised to the power 1, then 2, all the way to raised to the power n minus 1. I'm going to put a transpose signal because the vectors in our discussion will be column vectors. You may be wondering, where did the minus sign go? Well, the minus sign appears when we start talking about the complex conjugation, because remember, the dot product will always involve the second component being complex conjugate, and this is where the minus sign comes from in our formulas. So I'm going to represent the numbers that are being raised to different powers here as little wk, and these numbers have several useful properties. For example, if I take wkth number and multiply it by wjth, then this is going to be e to the 2 pi I k over capital N times e to the 2 pi I jth over capital N, and I can write it as a single exponential 2 pi I times k plus j over capital N, so it is a number w with the index k plus j. Also, if I take wk and raise it to the power j, then I get e to the 2 pi I k over capital N raised to the power j, which is the same as e to the 2 pi I k times j over n. So it is the number w with the index k times j. So you see the numbers w have logarithm-like properties. In particular, any wk raised to the power capital N is going to be e to the 2 pi I k times n over n, so it's going to be e to the 2 pi I k, and as a complex number this will always going to be 1, just like any number raised to the power of 0. Also, we know that these numbers are periodic, so for example, if you take wk and shift index to the positive or to the negative side by capital N, you're going to get exactly the same as wk. So this is e to the 2 pi I k plus or minus n over n. So this is going to be, if I break it up, is e to the 2 pi I k over n times e to the plus or minus 2 pi I k. The second number is always going to be 1, so it's e to the 2 pi I k over n, and therefore it's the same as wk. So shifting the index of w's produces the same numbers. What is also interesting is that negating the index k actually creates complex conjugates. Specifically, w of minus k is e to the minus 2 pi I k over n, which is the complex conjugate of the number e to the 2 pi I k over n, with a big bar in the top, and that's just wk bar. In particular, if we add n, w of n minus k is going to be the same as wk bar. We're going to create a certain effect for our discrete Fourier transform, and that we will have to account for it. So with this new notation, we can express the Fourier transform as just an inner product with the vectors wk. So f hat k is going to be the same as the vector f in the inner product with the vector wk. In a way, we represented the discrete Fourier transform as the vector of inner product, so they are somewhat like coefficients, and wk are somewhat like basis vectors. If we can show that these basis vectors are orthogonal to each other, then we can use the framework of the orthogonal basis to create a reconstruction formula. And in fact, the vectors wk form an orthogonal basis. So a little typo right here, they form an orthogonal basis. That is, these vectors are orthogonal to each other and their norms are non-zero. So wk in the inner product with wj is 0 if k is not the same as j, or capital N if k equals j. The proof of this fact is extremely simple. The inner product of wk with wj is the summation. Let's use the index m going from 0 to n minus 1, and the components of wk are the number wk raised to different powers multiplied by the corresponding components of the vector wj. However, the wj components need to be conjugated because that's the definition of the inner product within the spaces with complex numbers. So this is the same as the summation as m goes from 0 to n minus 1 wkm multiplied by w minus jm. So this is the summation as m goes from 0 to n minus 1, again using the properties of these numbers. The indices are going to add, so it's w with the index m times k minus j. So again, using the same properties, this is the same as the summation of wk minus j raised to the power m, and we know the summation formula for this. This is wk minus j raised to the power n minus wk minus j raised to the power 0, which is going to be 1, divided by wk minus j minus 1. I'd like to point out that this formula is only true if the denominator is non-zero, which means that k should not be the same as j. Well, again, using the properties of the w numbers, any w number raised to the power n is exactly 1, so we have 1 minus 1 divided by wk minus j minus 1, so it is 0. If k equals j, then the inner product of wk with itself is going to be the sum. M goes from 0 to n minus 1 wk raised to the power m times wk bar raised to the power m, and that means that this is the sum as m goes from 0 to n minus 1 of the numbers w0, which are all 1s. So this is just going to be the sum m goes from 0 to n minus 1 of 1, and sum of exactly n 1s has to be n. So we can say, if I have a vector of samples and I computed its discrete Fourier transform, then knowing the discrete Fourier transform, I can recreate my original vector by just adding up the coefficients times the vectors. Since the inner product of this is n, I have to divide by the norm squared to make it work. So it is 1 over n times the summation as j going from 0 to n minus 1. I take f hat j times e to the positive 2 pi I j over n times k. I'd like to point out that the definitions of the discrete Fourier transform also differ depending on who you're talking to. Engineers, mathematicians, computer scientists all have different definitions of this Fourier transform depending on what is most convenient for their particular application. So be careful when you're using software packages because their definition may be different from what you think it is. And again, the definition of the discrete Fourier transform in mathematics is also different from the definition I gave you. The differences are where do you put the minus sign, which exponentials are negated and which exponentials have a positive sign, and also whether or not you put 1 over n, 1 over square root of n in front of each particular sum. So for us, I'd like to stick to the definition that aligns itself with the definition of the continuous Fourier transform that we gave, where there is no coefficients in front of the integral and all of the coefficients are in front of all of the inverse functions. And the integration is performed with the negative exponentials to get the Fourier transform, and the positive exponentials restore the function. So let's compute a few Fourier transforms. So here I have a few examples of signals, and let's go through them in order. So for f hat k would be the summation as j goes from 0 to, in this time we have 8 components, so it's going to go up to 7. Going to be 1 times e to the power I 2 pi k over 8 times j. So I can write it as a summation. J goes from 0 to 7 of simply wk raised to the power j. We already know the formula for it. It's going to be exactly 8 if k equals 0, or 0 if k is not 0. So the vector of the Fourier transform is just 8, 0, 0, 0, 0, 0, 0, 0 transposed. How can we interpret this? Well, we can see that f is a signal that doesn't oscillate. The only frequency that's present in it is the 0 frequency. And my discrete Fourier transform kind of verifies this fact that this function doesn't oscillate. The non-zero frequencies are not present in that signal. The other functions are a little bit more complicated to do by hand, so I'm going to switch to Mathematica and continue there. So my next signal is powers of -1, so I'm going to tabulate the number -1 raised to the power k, and I'll let k go from 0 to 7. I'm going to say that this is my vector g. So next thing I need to do is I need to create a vector with the exponentials. So it's minus I times 2 pi k times j divided by capital N is 8. And j will go from 0 to 7. And then I will need to have a dot product of G with WK. The dot product in Mathematica is a dot operation, but I must warn you that this dot product does not compute the complex conjugate of things. So G in dot product with WK is just going to be a summation of these things multiplied together. And all I need to do is to compute this for different K. So let me call this G hat and plot it. The Mathematica has a command list plot and also needs the real numbers only, so I'm going to compute the real part of G hat and at the same time plot the imaginary component of G hat. Notice an interesting thing, that we only had 0 in a few components, and then when you actually compute some of them, they zero out themselves. List plot does not automatically adhere to our convention to start numbering things from 0, and we can see that the fourth component that corresponds to the index k equals 4 is non-zero, which means that there is a high frequency of oscillations and then all other frequencies are not present. This is again expected because our signal oscillates between plus or minus 1 quite quickly. Let's look at another signal that I have, which was twice as slow oscillations. Things from going from 1 to 0 to -1, then to 0. I can create that signal by just computing cosines of k times pi over 2 and let k go from 0 to 7. That's exactly the signal that I have in my notes. So again, computing U hat as an inner product of U with WK and then tabulating it as k goes from 0 to 7. Gives us a slightly conflicting picture. That it seems that according to the discrete Fourier transform, there are two frequencies present here. One that corresponds to the index 2 and one that corresponds to the index 6. So do we have two frequencies, one very low and very high? Not really. Remember that the discrete Fourier transform is periodic. And also, whatever corresponds to the higher frequencies is what corresponds to the negative frequencies in the signal. So the higher frequencies region right here corresponds to the negative frequencies that should be on the other side of the spectrum. What do I mean by that? Well, the numbers WK for very high k are the same as the complex conjugate of W of n minus k. So if I have a frequency present for the index 6, that's the same as if I computed the inner product of the WK number with the frequency 8 minus 6, which means -2. We have a non-zero component for the frequency corresponding to the index 2, and we also have a component corresponds to the frequency -2, which if we think about are two same frequencies. What we'll see in all of the discrete Fourier transforms in terms of the magnitudes of the discrete Fourier transform are reflected around the middle. And when I try to reconstruct a continuous signal from my discretized signal, you will see how I will have to account for that. So don't be fooled by a very high index right here that corresponds to the index 6. That doesn't mean that I have a very high frequency in the signal. It actually means that it is a reflection of what was going on for the frequency with the index 2. The last signal that I had here was a signal that rises from 1 to 4 and then goes back to 0. That signal I will have to enter by hand. and then I compute its Fourier transform by computing the dot product with WK, and then tabulate with K going from 0 to 7. It's quite a lot of frequencies are present in this signal. So last thing I want to do is I want to show that all of those transforms are actually invertible, and we get our signal restored back when we apply the inverse Fourier transform. For my example f, there's only one non-zero component, and so therefore fk should be the summation as j going from 0 to 7 of f hat j multiplied by e to the positive 2 pi I k j over 8. But since only one component is non-zero and there's also 1 over 8 in front of the summation, we have that every fk is 1 over 8 times 8 times e to the 0, so therefore it's just 1 for every fk. The signal is restored perfectly. For that example I computed with Mathematica, I can restore the signal by doing the summation there. So g hat was the Fourier transform vector. So what I need to do is I need to compute a different wk vector that will denote wk inverse, which is going to be the same exponential factors, except that I'm going to take away the minus sign. So in order to compute the inverse, I would have to take 1 over 8. I would have to compute the inner product of g hat with the inverse of wk. I would need to tabulate it for k going from 0 to 7. And I know I'm going to get some difficult results with the exponentials, so I'm going to ask Mathematica to simplify it before presenting me with the mass of complex exponentials. And I have my signal back in its original form. The same can be done with the u hat. So it's 1 over 8 because there were 8 samples for each one of them. I'm going to take u hat and compute the product with the inverse of wk. And I get my signal perfectly back. I'd like to point out one interesting thing. As I said, the frequencies that we see for the higher indices are the same as the negative frequencies. So what if I compute my inverse slightly differently? So what if I'm going to compute the inverse component, a second version of it, so this component was computed when j was exactly 4, which would be the same as the frequency negative 4. So that's going to be minus ik pi when I simplified things. This component was computed when j was 5, so it's the same as letting j to be negative 3. This component was computed when j was 6, and then it was divided by 2. That's what made it 3. And so it's the same as making it negative 2. When simplified, that's going to be negative 1 right here. This was computed when j was 7. It's the same as j being negative 1, and then it simplifies into minus 1/4. Try to restore the signal with my newly defined inverse, still get the same signal back. And technically, it's more correct to use negative frequencies, as we're going to later demonstrate. So let's restore the last signal that we have. We had v hat and the signal is restored perfectly. And again, if I try to use negative frequencies, I restore exactly the same signal. The last thing I want to talk about is the effect that the sample has on the continuous counterparts of my functions. I'm going to consider a function that's defined in interval 0 to 6. It's 0 at exactly 0 and 0 at exactly 6. I'm going to assume that the function is 0 everywhere outside interval 0 to 6. And therefore, the only region that I need to sample it is the region from 0 to 6. So I'm going to take the frequency to be 1 Hertz and then sample it at every integer. So the f vector will be the table of samples, and then the double n is the length of this vector. I'm going to define the quantities wk in exactly the same way I defined them before. I'm going to compute the discrete Fourier transform of f. And I'm also going to compute the continuous Fourier transform of f just to see what is the actual Fourier transform of the function f. If I plot discrete Fourier transform, well, since I only have 7 coefficients, there's not much to see. But I do know that these are just samples of the actual Fourier transform of the function, but not the Fourier transform of the function f of t, but the Fourier transform that's been periodized. So what I'm doing here in these two images is I'm plotting the discrete Fourier transform, the same thing that I just computed, but this time treating k as a continuous variable. Well, this command only adds these little dots that indicate where the samples of the discrete Fourier transform that I computed above land on this graph. So it seems like I have created a periodic function that has nothing in common with the actual Fourier transform of the function. But I'm going to demonstrate that it actually does have something in common. If I periodize the Fourier transform above, so I take the Fourier transform, I shift it by the proper amount, and then add the shifts together, then what I actually end up with is the exact same graphs that I have for my discrete Fourier transform, but plotted as a continuous function of k. So what actually happens, as I said, is that the actual Fourier transform is being periodized. And the way to separate these two Fourier transform, these periods away from each other, what I will have to do is I will have to cover a wider range of frequencies, which means, as I said before, that I have to increase the sampling frequencies of my signal. If I try to restore my signal, but the function is nothing like the function I started with, it has the oscillations that were not supposed to be there. Those oscillations are exactly the aliasing effect that I mentioned before. The other graph I have on the right is the graph of the complex component of my restored signal, and as you can see, it hovers about 10 to the negative 16, so it's practically zero. So where did these oscillations come from? They came from not enough separations when I periodize this Fourier transform. When I add shifted copies of each other, they overlap and they add to themselves, and they get those imaginary frequencies now present in my signal. So what if I sample with a different frequency? Say, what if I decrease the interval between each sample? So now I'm making the frequency twice as high. I'm sampling instead of at each integer, I sample at each half. So I get more samples, now 13 samples. I have to redefine WK, I have to recompute the discrete Fourier transform. The Fourier transform, the continuous Fourier transform is the same, so there is no need to recompute it. I can see I have more samples of my discrete Fourier transform. And if I plot the discrete Fourier transform as a continuous function of k, you can see that I still have a periodic repetitions of my Fourier transform, but they are actually more separated, that I actually more or less separated the copies of this function enough so that they don't interfere with each other. You can see the imaginary part is being more or less correctly represented here. So again, with this new increased frequency, if I start periodizing the actual Fourier transform we computed before as a function of omega, then I get exactly the same picture as I have for the discrete Fourier transform as a continuous function of k. And then if I try to recreate the signal, then I get my function recreated almost perfectly. I do see a little bit of a ripple right here at the tails. Again, I still have some cross-contamination of the high frequencies of this function, sort of migrating into a lower frequency range right here, because I don't have the separation quite perfect. If I increase in frequency and start doing it 3 times per integer interval, then I will have a lot better separation. Compute more samples on my Fourier transform. Better separation of my periodized Fourier transform. My periodized Fourier transform is a lot more separated now. And I recreate my function with a lot better accuracy. What if I'm going to compute now, instead of simple sample at every integer, I'm going to make 4 samples per every 3 integers. My function recreated not exactly. Notice though that the dots are exactly where they are supposed to be. Whether or not I have a good enough frequency of sampling, bad enough frequency of sampling, I recreate the samples almost perfectly. The dots are exactly where they're supposed to be. However, the actual continuous function that these dots will represent will be a slightly warped copy of the actual function I started with. So it is important to sample the signal at the right frequency. Increasing the frequency, say sampling 4 times per integer, will create enough separation of the copies of my Fourier spectrum, and the function will be restored with very little distortion. So this effect of sampling frequency, this sort of a periodizing of the Fourier spectrum that you do with different sampling frequencies, is very important to understand when you're working with digital signals. What I would like to add is this discussion was completely optional. The main takeaway of today's lecture is that the discrete Fourier transform is defined as a sampling process with the formulas that I gave you. A discrete Fourier transform does have interpretation of showing you the frequencies of the signal. So where the discrete Fourier transform have a large absolute value, that probably indicates that there is a frequency present in the signal that you're sampling. Also, that the discrete Fourier transform is perfectly invertible, is that no matter what sample frequency you use, you will recreate your samples from the discrete Fourier transform perfectly. You might not be able to represent the function in between the samples that you recreated, but that's not really important. I'd like to point out that here I table e to the 2 pi I k j, with j going from 0 to 1/2 of the interval, and then for the rest of the frequencies I make j to be negative. If I don't do that, I will see superfluous oscillations in my signal. Without the discrete Fourier transform samples the periodized Fourier spectrum in a way that it goes from 0 frequencies to very high frequencies, and then this part, which should have been repeated on the negative side, is actually sampled in the space of very high frequencies. That's something that you should be aware of. So when you're restoring your signal, if you want to restore a continuous signal, you cannot use those high frequencies in your restored signal. You have to opt for negative frequencies, and this way you will restore the signal perfectly. There's 2 more lectures on the discrete Fourier transform, 1 lecture on discrete convolution, and 1 lecture that will be just an overview of the applications of the discrete Fourier transform and fast Fourier transform, which is the very quick, computationally efficient way of computing the discrete Fourier transform. And then after that, we'll switch to partial differential equations. That's it for now. Have a good rest of the day, and I'll see you in our next video.